Hello, guys. Welcome to Ramta Solutions. Welcome to your grade 12 Physical Sciences Chemical Equilibrium. Today's video is Introduction to Chemical Equilibrium. So this video will be more to do with definitions that you come across in this topic, and of course, a brief introduction of what this topic is about. So now, let's imagine this. Let's imagine this. Um, you do know that there are reactions that look like nothing else is taking place, no matter how long the reaction is taking place, right? Let me note this. There are reactions that look like nothing else is taking place, or that look like nothing is taking place, not nothing else, that look like nothing is taking place, no matter how long they are left to proceed, no matter how long they are left to proceed. All right. So, for example, let's say you had a reaction, not to say that it has stopped or all the reactants have been used up, but rather there are still reactants. And in the final solution or in the solution, you have a bit of your reactants, you have a bit of your products, but the reaction is not changing. It's still on the same level. This is where we will be talking chemical equilibrium. Okay. This is where we will be talking chemical equilibrium. Now let's also imagine this. Now, what happens when nothing is happening, but the reactants are still present? Oh, so when nothing is happening, but the reactants are still present. So here, I'm basically saying there is there is no reactant that is called a limiting reactant here. Okay, there is no reactant that is a limiting reactant. Okay, there is no reactant that is a limiting reactant. All the reactants that you started the reaction with are there, and the product is still there. Now this is where you're talking chemical equilibrium. Okay, this is where you're talking chemical equilibrium. Now when this happens, right, when this happens, it is because the reaction takes place in the forward and the reverse direction. It is because the reaction takes place in two directions. The reaction takes place in two directions. And what are those directions? The forward and the reverse direction. The forward and the reverse direction. Okay. Takes place in these directions. So for example, let's say we have substances A and B giving us products C and D. Of course, the capital letters A, B, C, D being the substances, and the small letters being the coefficients in a balanced chemical equation. And then you can also have this. Now, what do you see? This one here, we call it a forward reaction. This one here, we call it a reverse reaction. Can you see this? So what is happening here? With the forward reaction, it's the one that we know. You are forming the product that we're expecting. But then it turns out that somehow this product can also form the reactant back. This is where we talk of reversible reactions. So these kinds of reactions, we call them reversible reactions. These kinds of reactions are called reversible reactions. Are called reversible reactions. Let me highlight them. Okay, they are called reversible reactions. Okay, they are called reversible reactions. We're going to give you a definition later. Okay, so example of reversible reactions. Examples of reversible reactions are in a closed system, you can have evaporation and condensation. All right, in a closed system, you can have evaporation and condensation. Now let's get to biology. Hemoglobin. Let's talk hemoglobin. And oxygen. And what else? And oxyhemoglobin. Okay, and oxyhemoglobin. Okay, so these are the examples of reversible reactions that we know naturally. I'm going to give you the chemical reactions to show these reactions. Okay, I'm gonna show them rather as a chemical equation. Okay, I'm gonna show them as a chemical equation later. Okay, now we are then going to give you some definitions. Okay, we are then going to give you some definitions. Let me go to the next page. Definitions that you're going to come across in this topic are: one, open system. You need to know what is an open system. Here, this is a system that continuously interacts with its environment. Okay? These definitions are definitions according to the Department of Basic Education. Okay? Where possible, I will try to expand on them. Okay? That continuously interacts with its environment. With its environment. Okay, this is an open system. So, with an open system, what we're saying here, we are saying that basically this is a system where matter can enter the system. Okay, now there's a system where matter cannot enter the system, and this gives us or leads us to defining a closed system. So, what is this one here? So this one here is a system that is isolated from its surrounding. Okay. Sorry, that is isolated. That is isolated from its surrounding. Okay. That is surrounded from its surrounding. Okay. So this is the system that is isolated from its surrounding. Okay. So what we are saying here is that this is a system. Again, you can use the definition that says it is a system where substances cannot leave or escape the container. A system where substances cannot leave or escape the container. Okay. Okay. So now let's expand on this briefly. So here, when it comes to the closed system, energy can enter or leave the system, but matter cannot. Okay? But matter cannot. Now, when it comes to the open system, we are saying that energy and matter can enter and exit the system. Okay? Perfect. Now we're going to talk about the reversible reactions. I did introduce them earlier, but I didn't define them. All right, I didn't define them, but I think I did in a way, but not convincingly so. All right. So as you can see, look at this. We said it is because the reaction takes place in two directions. There is the forward and the reverse reaction. So this therefore tells us that a reversible reaction takes place in both directions. Right? So the DBE definition is this. Um, these are reactions that um, can proceed. Maybe let me put it like that. Reactions that can proceed in both the forward and reverse direction. In both the forward and reverse directions where in a closed system. Okay. But let me not say that reactions that can proceed in both the forward and the reverse direction in the same conditions. Okay. In the same conditions. This is the definition of the DBE. In the same conditions. Okay. In the same conditions. Okay. In the same conditions. So yes, reversible reactions are reactions that can proceed in both the forward and reverse direction. You can also leave it there. It's okay. All right. Now let's talk of chemical equilibrium. Let's talk chemical equilibrium. Okay, let's talk chemical equilibrium. Now, chemical equilibrium, I did give you a scenario earlier, right? I did give you a scenario earlier, isn't it? I did give you a scenario earlier, but now I want to give you a definition. So, chemical equilibrium is a stage reached, okay, is a stage reached by a reversible reaction, okay? Just hold, we're not done. It's a stage reached by a reversible reaction, okay, in a closed container. So, closed system in a closed container. So, this is a closed system, right? In a closed container where the rate of the forward reaction equals the rate of the reverse reaction. Okay. Where the rate of the forward reaction equals the rate of the reverse reaction. Oops, let me write reaction in full. Equals the rate of the reverse reaction. Okay, so this is the definition of chemical equilibrium. This is the definition of chemical equilibrium using rates. Now, I'm going to give you another one using concentrations or amount of substance. So it'll be a stage where the quantities or concentrations quantities or concentrations of reactants. Oh, we have come to the bottom of our page. Quantities of concentrations of reactants and products remain constant. Okay, remain constant. Okay, so this is the second definition of chemical equilibrium. So I believe this second definition tells you about the opening example we had. All right, it tells you about the opening example we had. It explains it, isn't it? Perfect. Now we then going to talk about a principle. We then going to talk about a principle which we say is this word is French. So in French they call it les chateliers. Okay, so it's les chateliers, right? So this is the principle we need to know of by heart. So in in French it's le Chatelier's principle. All right, le Chatelier's. But because we don't speak French, we must say le Chatelier's. Right. So le Chatelier's principle. So le Chatelier's principle. I know it's LE, but we must read it as lo. So le Chatelier's principle. So this one says your system is already at equilibrium, meaning the amount of products and reactants are remaining constant, and so are the rates of the forward and the reverse reactions are equal. Now, this system wants to continue like that. It doesn't want to be disturbed. But because there are people who like disturbing our peace, they will always try to they will always try to change that system. Now, when that happens, because systems like remaining constant or remaining the same, they will try to create a new equilibrium. Might be higher than the previous one or lower than the previous one. So what do they do? When you disturb, say your disturbance is increased, the system will react by decreasing. If you decrease, the system will react by increasing. Okay, so Le Chatelier's principle says, and this is according to your DBE, guys, okay? But what I just said is basically it. When a system at equilibrium is disturbed, when a system at equilibrium is disturbed, when a system at equilibrium is disturbed, remember the disturbances, you will learn about them later. When a system at equilibrium is disturbed, the system responds by opposing that disturbance. Okay, so let's see. How can we put it like this? The system will, maybe let me use this definition where they say when a system at equilibrium is disturbed, the system will reinstate. Okay, the system will reinstate. Okay, will reinstate a new equilibrium. Okay, it will reinstate a new equilibrium by favoring, by favoring a reaction, or maybe not A, but by favoring the reaction that opposes the disturbance. Okay, that opposes the disturbance. Okay, so let's read it once again. So we are saying when a system at equilibrium is disturbed, okay, when a system at equilibrium is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. Or simply, when a system at equilibrium is disturbed, the system responds by opposing the change and a new equilibrium is established. You guys get it, right? So that is your chemical, that is your Le Chatelier's principle. Okay, that is your Le Chatelier's principle. Okay, so now we then need to note a few things like when it comes to equilibrium, you can have two kinds. You can have homogeneous equilibrium. Let me state that as well. You can have homogeneous equilibrium. By now, you know, whenever you see homo, you know it means things of the same kind. All right? Hetero, you know it means two different kinds. All right? So homogeneous equilibrium, what is it? What is homogeneous equilibrium? You guys now have an idea, right? So when it comes to homogeneous equilibrium, this is equilibrium established by substances of the same kind, okay, or same phase, okay? So this is equilibrium established by substances of the same phase. Let's say same phase. Of the same phase. Okay. Then let's talk heterogeneous equilibrium. Let's talk heterogeneous equilibrium. Heterogeneous equilibrium. So what about it? Because this one will say it is equilibrium established by this is equilibrium established by substances of different phases. Right? By substances of different phases. Right? By substances of different phases. Okay, by substances of different phases. Okay, this is your heterogeneous equilibria. Okay, now we also need to talk about dynamic equilibrium. We also need to talk about dynamic equilibrium. All right, we also need to talk about dynamic equilibrium. So when we talk about dynamic equilibrium, we are going to be referring to the rate. Okay, we're going to refer to the rate. So with this one, you need to see the same definition of equilibrium. Okay, so this one is the same definition, has the same definition as chemical equilibrium. Okay, same definition as chemical equilibrium. Okay, this has the same definition as chemical equilibrium. You remember we defined chemical equilibrium as the stage reached by a reversible reaction in a closed container where the rate of the forward reaction equals the rate of the reverse reaction. So we will give it the same definition as chemical equilibrium, and I'm going to say with regard to rate. Okay, I'm going to say with regard to rate. Okay, I'm going to say with regard to rate. So your chemical equilibrium is also called dynamic equilibrium. Why? Because reactions are still occurring in both directions. This is why it's also called dynamic equilibrium. I repeat, it's called dynamic equilibrium because reactions are still happening in both directions. You remember the directions? Forward and reverse directions. All right. Now, let's go back. We did talk about reversible reactions. All right. We did talk about definitions. Okay. We did talk about the reversible reactions. All right. So now I want us to show how to represent reversible reactions. Okay. Now I'm going to show you how to represent reversible directions. So representing reversible reactions, representing reversible reactions, we use the left-right harpoons. Okay, so they are represented by the sign which you are going to see. You see, the left-right harpoons represent reversible reactions. So that reaction that we had, A reacting with B to form C and D, and when C can react with D to form back the reactant, right? These are equilibrium reactions or are reversible reactions, right? So to represent them, instead of writing these two individually, what we're gonna do is we can just use one line and say this is substance A reacting with substance B, a reversible reaction. Can you see that? Now this is how you represent reversible reactions. Okay, this is how you represent reversible reactions. Okay, now our examples, one, evaporation and condensation. Let's represent it. Evaporation and condensation. So we will say in a closed container. Okay, in a closed container, we will have, for example, liquid water. When it evaporates, it will form gaseous water, which you call water vapor, isn't it? In the same way, water vapor can condense to form liquid water. Do you guys see that? Now, this is a reversible reaction. Okay, this is a reversible reaction. All right, this is a reversible reaction. I did give you hemoglobin in blood. Let me just say hemoglobin in blood. Is that okay? Hemoglobin in blood. So hemoglobin in blood reacts with oxygen, right? Reacts with oxygen. So let's try it. So let's say now hemoglobin HB, aqueous phase, plus oxygen gas. Let's still say, because it's in blood, let's say oxygen aqueous, reversible reaction, oxyhemoglobin, again aqueous. That again aqueous. Do you guys see this? Now, what you are seeing here is this. In lungs, right? In our lungs, you will see the forward reaction, which is hemoglobin plus this guy here, giving you oxyhemoglobin. And then in the tissues of our body, in tissues, you're gonna see the reverse reaction. All right, you're gonna see the reverse reaction. Or what's happening is, or what's occurring, not happening, what's occurring is the reverse reaction. In fact, I should have said gaseous species. Okay, so these the examples of reversible reactions that we have. As you can see, these are in equilibrium. Okay, these are in equilibrium, and this is all you need regarding chemical equilibria. In the next video, we are going to be looking at Le Chatelier's principle. Okay, in the next video, we are going to be looking at Le Chatelier's principle. We're going to decide how we go about it, because it's a lot, but we're going to decide how we go about it. Okay, that's it, guys. I hope you guys enjoyed this. So see you next time, and bye bye.